Alright, this is chapter 16, electric charge and electric field. So we know that electric charge is conserved. What does that mean? That means that when we rub two objects together, like yesterday when you were rubbing your rabbit fur and the styrofoam, one object gets a positive charge and the other must get a negative charge. So charge is neither created or destroyed. If something loses electrons, another object gains electrons. It's not like the electrons just poof into nothing. We have different types of materials, conductors and insulators. It's a little more complicated than this, but for right now, this will suffice. So we know conductors allow charge to move freely, and that includes metals. Insulators, almost no charge flows, but sometimes it can under the right circumstances, and that's pretty much most other materials. There are some materials called semiconductors that are more complicated. You'll learn about those later in your physics life. So if I have two charged objects, or sorry, excuse me, one charged object and one neutral object, if I connect them with a conductor, then the charge will separate between the two. It will travel through the conductor and spread out. If I can attach them with an insulator, the charge will stay on the conducting or the charged sphere. So we can charge objects in different ways. One way to charge an object is by conduction. So let's say that I start off with a neutral metal rod. I take a charged object and I touch it to the neutral metal rod. That touching causes the charge on the metal object to spread onto the charge or onto the neutral metal rod. So that is charging by conduction when they actually touch. Now notice that the positive charge will move onto the rod, but it's really the negative electrons that are moving off of the rod onto the charged object. We can talk about the motion of positive charge even though we know that the neutrons are not actually moving. Oh my gosh, the protons are not actually moving. Sorry. So the key thing for conduction is contact. We can also charge things by induction. So here's an example of charging by induction. Let's say that we have a neutral object and it's attached to a ground. This is the symbol for ground, BT dubs, and you're basically attaching it to this infinite source of charge. So positives and negatives, lots and lots of them. And when I bring my charged object nearby, this negative is going to push away electrons. It's going to push away the negative charge into the ground, and it's going to pull the positive charge towards it. So that will result in a positive charge on this object. Then if I unattach the ground, so now I've unclipped the wire, suddenly my object is charged. So when I charge by induction, I don't actually touch the two objects. We can also charge by induction in this way. Let's say that I have a charged object and I have two metal spheres. And the metal spheres are touching each other. So they're touching and they're near this negatively charged object. So the positive charge is going to accumulate close to this negative charge, and the negative charge is going to be pushed away onto this sphere over here. Then if I separate these two, now I have a positively charged sphere and a negatively charged sphere. That is also charging by induction. So the original thing that was charged does not actually touch the objects that gain the charge in the end. We also, so when we have insulators, when a charged object is brought near an insulator, then we have a separation of charge, but the charges aren't actually moving across the insulator. We can't charge insulators by conduction or induction. The only way we can charge them is by rubbing them against another material, not just simply touching. But notice that when I bring this charged object near this material, this non-conductor, the charge separation, there is a charge separation within the atoms in the insulator. So the electron clouds are effectively shifting. So if I have this positively charged thing near this insulator, the electron clouds are going to be attracted to that positive charge, so they're going to shift towards the positive charge. That results in this negative charge that's on the surface of the insulator. But the insulator still has a neutral charge. Are you having fun yet? I hope so. We have Coulomb's law, which you are going to derive in a lab soon. The equation for Coulomb's law is F equals KQQ over R squared. This should look familiar. What does it look like? It should look like the gravitation equation, which is F equals G times MM over R squared. So gravitational force and the electric force or Coulomb force have a lot of similarities, and we'll talk about those in a second. So we should talk about this real fast. We know that two positive charges are going to repel each other. Two negative charges are going to repel each other, and a positive charge and a negative charge are going to attract each other. This is a really awesome place for Newton's third law questions. What if I had twice the charge on this one that I have on this one? How would the force that 2 puts on 1 compare to the force that 1 puts on 2? And what's the answer? They are the same. And if we look back up at the equation, we know that the force involves both of the charges. So the direction of the force will depend on where the charges are, but the actual size of the force is going to depend on both charges. So if 1 pushes on 2, 2 pushes on 1 with an equal force in the opposite direction because of Newton's third law. So this is going to follow Newton's third law as well. The unit of charge we're using is a coulomb. It has a capital C as its, what do you call that? Symbol. We also need to know Coulomb's, like proportionality constant in Coulomb's law, which is K, 8.988 times 10 to the 9th Newton meter squared over Coulomb squared. I usually just use 9 times 10 to the 9th because it's pretty darn close, and it's a lot easier to write. Just so you have an idea of how large a coulomb is, charges produced by rubbing are typically around a microcoulomb, so 1/1,000,000th of a coulomb, and that would be like you rubbing a balloon on your head and getting it to be charged or something like that. Coulomb's law strictly applies to point charges, which is important, and we'll talk more about that later. We also have superposition for point charges. So the forces that multiple charges exert on each other or other things, we're going to use vectors to add those up. So this is a force. Force is a vector. It's just like any other forces that we've learned about. If I'm looking for the force on Q3 from these two forces, I have Q2 here. So there's going to be a force on 3 from 2 pointing along the y-axis. And then my force from Q1 is going to point towards Q1. This is the force on 3 from 1. And notice that it has, this one has components in both the x and y directions. So to find the net force, I would add these using my vector addition knowledge. So I have my force on 3 from 2, my force on 3 from 1, and then this will be my net force right here. So I could find those components by breaking it up and adding it as we would any other force vectors. Electric field. This is a challenging topic. We talked a little bit about gravitational field, and a good way to remember stuff about electric fields is to think about gravitational fields. So we talked about how the Coulomb's law equation is very similar to the universal law of gravitation. This is because both of these forces are field forces. So the forces, remember, allow objects to interact without actually touching, and that's what the fields do, and then the fields also alter the space. Excuse me. So the space around these charged objects is actually changed because of the charges. We're going to set up this chart here, and this is helping you relate these equations to each other. So the nice thing about this is that it's kind of like your kinematic equations and then your rotational motion equations, how they all have a corresponding piece. Gravitational forces and fields and electric forces and fields have the same situation going. So if we have a constant gravitational field, like near the surface of the Earth, we know that that gravitational field is equal to the force per mass. So the gravitational force per mass. That's why we measure the gravitational field in newtons per coulomb. And then for electric field, we have the same situation. Electric field is going to be the force per charge, and Q is the symbol for charge. So if I have an object in an electric field which has a strength of 2 newtons per coulomb, that means that there's going to be a force on that object of 2 newtons for every coulomb of charge that's in that electric field. That's for constant fields. Now, when we have point charges, we're going to have a different situation, because as you get farther from the point charge, the electric field is going to change. Same thing if you think about the universal law of gravitation. When we were studying like how planets orbit, we had to use this equation, because as you get farther from the surface of the Earth or from the Sun, the gravitational force is going to change because the gravitational field is getting weaker as you get farther from the surface of the Earth or the Sun or whatever. When we use this equation, we're assuming that the gravitational field is constant. We're thinking about our everyday lives in which we are near the surface of the Earth. So there is, the same kind of situation for electricity. There are going to be situations where we have a constant electric field, and we'll learn about the specifics of those later. And then there are going to be times when we have point charges. So our electric fields are going to be different as we change our position. So notice we already talked about the comparison between these two equations. And if we cancel out the little mass, cancel out one of the charges, then we can get the equation for gravitational field around a mass, and then also the electric field around a point charge. So remember, this charge is the charge that creates the field, not the charge that's in the field. Just like this mass is the mass that creates the gravitational field, not the mass that's in the gravitational field. Let's talk a little bit about electric field lines. Electric field lines allow us to represent an electric field. They're not actually there. They're something that we use to help us understand the electric field. Electric field lines will point away from positive and into negative. They show the path a positive charge would take if it were placed at any given point. So if I put a positive charge right here, it would go zoom to that negative charge. When the lines are close together, the field is stronger. So notice these lines are closer to each other near the negative charge. As you get farther from the charge, they are farther apart. So the electric field is getting weaker. There's your full picture. Bam. One more page. Aren't you excited? Let's talk about electric field and the conductors. This is kind of challenging. So the static electric field inside a conductor is 0. If it were not, then the charges would move until it is. So let's talk about this. Let's say that I have a metal ring, and in this metal ring is a positive charge. So this positive charge obviously creates an electric field, and that electric field is shown by these lines like this, right? So the conductor has charges within it that can move and interact with this electric field. So as this electric field passes through the conductor, it causes these negative charges to be attracted to this positive charge, and then these positive charges to be repelled, so it creates a separation of charge within the conductor. So a negative charge accumulates on the inside of the conductor, and a positive charge accumulates on the outside of the conductor. And these charges will move until they have a separation. So the separation of these two charges is creating its own electric field. And that electric field vector, this little blue one, cancels out the red one. And so the net electric field within the conductor is 0. Pretty fun, huh? I know. All right, one more thing. Yeah, one more thing. Electric field is perpendicular to the surface of the conductor. Again, if it weren't, charges will move until it is. So if the surface is curved, then the electric field vector is going to always be perpendicular to the surface. And we'll practice drawing some electric field vectors of different things. But that is an introduction to this concept. I hope you enjoyed it. Now I just have to figure out how to turn it off. Here we go. Bye. Bye.